Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. Hey everyone, so GoogLeNet or Inception V1 is one of the finest and classic neural network architecture, and in this video I will implement GoogLeNet from scratch with PyTorch. Let's jump in. First, let's see what was the problem that GoogLeNet or Inception V1 tried to solve. So if we look at this picture, there are three pictures of cat, and the area occupied by the main subject, that is a cat, is different in each of the three images. So here the point is the salient parts of the image can have extremely large variation in the sizes, and because of these huge variation in the location of the information, choosing the right kernel size for the convolution operation becomes tough. A larger kernel is preferred for information that is distributed more globally, and a smaller kernel is preferred for information that is distributed more locally. Now, to solve this problem and to capture the local features, if I use small kernels and build a very deep neural network, that will be prone to overfitting, and also deep neural network is very difficult for gradient passing because that will be subject to gradient vanishing problem. And on the other hand, if I use large kernels and just naively stack large convolution operations on top of each other, that will be computationally very expensive. So the solution: why not have different filters with multiple sizes operate on the same level? And that would result in a network which will become slightly wider rather than deeper. So that's how the authors of GoogLeNet or Inception V1 propose this Inception module, what we see in the image. Here it performs a convolution on an input with three different sizes of filter: 1 by 1, 3 by 3, and 5 by 5. Additionally, a max pooling is also performed. The output are concatenated and sent to the next Inception module. Let's see if we can understand these a little bit more intuitively. So in images, correlation among the features tend to be local, and if I use just a 1 by 1 filter, what we see here, then that will cover very local clusters. Now if I use a 3 by 3 filter, that will cover a little bit more spread out cluster, what you see here, that is on the right side here. Now if I go even higher, that if I use 5 by 5 filter like this, that will cover even more spread out clusters with this larger kernel size. So in the Inception module, we are going to use all of them, that is 1 by 1, 3 by 3, and 5 by 5, to capture different sizes of cluster size, that is different areas of features in the image, and then concatenate it on top of each other, something like this. So that's what kind of this image kind of intuitively shows that I have the previous layer, then it goes to through these all different sizes of kernel, 1 by 1, 3 by 3, and 5 by 5, and then that gets concatenated. The result of applying these filters gets concatenated, and then that result goes to the next layer. So that's kind of the basic intuition of the Inception module. Now here I'm looking at the original paper that was published in 2014, and the name of the paper is Going Deeper with Convolutions, and I would say this is one of the most well-written paper, that is you can pretty much implement Inception V1 or GoogLeNet by looking at some of the diagrams of the paper. It was so well explained in the paper. Now on the architectural details, the key feature of this paper is this Inception module. So here in this image on the left, you see the naive version of the Inception module, and on the right we see a slightly modified and slightly more advanced version of the same Inception module. So in the Inception module, 1 by 1, 3 by 3, and 5 by 5 convolutions and a 3 by 3 max pooling is performed in a parallel way at the input, and the output of these are stacked together to generate the final output. The idea behind is that the convolution filters of different sizes will handle objects at multiple scale better. So the Inception module is different from previous architectures such as AlexNet, ZFNet, etc. because in those architectures there is a fixed convolution size for each layer. In theory, you can have as many filter sizes as possible in your network, but the Inception architecture is restricted to filter sizes of these 1 by 1, 3 by 3, and 5 by 5. The small filters help capture the local details and features, whereas spread out features of higher abstractions are captured by the larger filter. And to these three filters, a max pooling layer of 3 by 3 was also added because historically it has been shown a pooling layer improves the result. And now on the going further into the architecture of GoogLeNet, let's look at the most popular diagram that they have given in their paper. So this one I'm talking about, this vertical one, and all these red and yellow thing that you see, that I have put in as my annotation to understand it better. So this diagram is so powerful that to build the entire architecture, you just need this diagram, and then you can build the entire architecture because everything is given here. And that's why they also have named it very aptly that this is GoogLeNet network with all the bells and whistles. So let's look into these in detail. So this is the start, the input, and then initially I have few conf layer and a max pool. I'm naming them like this is the stem. This is the starting stem of the entire branches and the entire tree. And after this initial conv layer and max pool, I have my first inception layer. So the inception layer is these wider regions where a parallel operation or parallel convolutions will go on with 1 by 1 filter size, 3 by 3 filter size, and 5 by 5 filter size, and also max pool. So I have total 9 blocks. You can count them like this: 1, 2, 3, 4, 5, 6, 7, 8, 9 blocks. So I have put these curly braces to them, and I also have a side structure. They are naming them auxiliary classifier. I will talk about the auxiliary classifier in little bit in detail in a second. But here, looking at the diagram, there are these two blocks. They are these auxiliary classifiers. So here I have one auxiliary classifier and the second one. That's it. So the entire architecture is 22 layers deep, 27 including the pooling layer, and it uses average pooling at the end of the last inception module, and needless to say that it is pretty deep classifier. Now the same architecture is also very well represented in this diagram here, which indeed will be extremely important while building the architecture from scratch. This diagram here, all the sizes, input sizes, output sizes, and the filter sizes, etc., is detailed very well. So another interesting addition to the architecture is to change the second last fully connected layer. Let's look at the diagram. Second last fully connected layer with an average pooling layer. This layer spatially averages the feature map, converting 7 by 7 into 1024 input to 1 by 1 into 1024. So I'm talking about these one here, average pool. And if I go back to the diagram here, then we will see that these converts that layer spatially averages the feature map, converting 7 by 7 into 1024 input to 1 by 1 into 1024. And doing this not only reduces the computation and the number of parameters by a factor of 49 of the network, but also improves the accuracy of the model, improving the top one accuracy by 0.6% according to the paper. And this average pooling layer is finally followed by a normal fully connected layer. This one I'm talking about with 1000 neurons and 1024 by 1000 parameters for the 1000 ImageNet classes, because they implemented this network on ImageNet dataset. Now let's quickly talk about these auxiliary classifier. We have two of them in the network. Let's zoom out and view their position. So in my entire architecture, starting from here and ending here, these are the two auxiliary classifier I have, and let's see what they consist of. So first, auxiliary classifier are type of architectural component that seek to improve the convergence of very deep networks, because like we saw that this entire structure is 27 layers deep with the max pooling included, and so being so deep, it is subject to the vanishing gradient problem. So there has to be some way to control the vanishing gradient problem in this kind of very deep network, and auxiliary classifier to some extent serve that purpose. They are classifier heads we attach to layers before the end of the network, and the motivation is to push useful gradients to the lower layers to make them immediately useful and improve the convergence during training by combating the vanishing gradient problem. To prevent the middle part of the network from dying out, the authors introduced these two auxiliary classifier indeed. They essentially applied softmax to the outputs here, to the outputs of two of the Inception modules, and computed an auxiliary loss over the same levels. And looking at this diagram, the auxiliary classifier layer are connected to the output of Inception 4A, that is this one, and Inception 4D, that is this one. And going back to this tree diagram, so on the architectural details of each of these classifier. So the auxiliary classifier, first will have a 5x5 filter size and average pooling layer. Then I will have a conv layer with 1x1. Then a fully connected layer, and finally I will have a softmax here, and the same structure for the other one as well. Yeah. And so yes, so we in my Scratch implementation, I will have this exact structure implemented in a second. Now if you look at the whole structure, the whole architecture in a single view, you can see that these two auxiliary layers are kind of positioned in the middle, or kind of in the intermediate in the entire architecture, and that intuitively makes sense. So what the authors of this paper kind of explained is that they recognize the fact that it's not only the features of the final layers that will carry all the discriminatory information, but intermediate features are also capable of discriminating different labels. And most importantly, these intermediate feature information is more reliable, since they are extracted from earlier layers in which the gradient carry more information. Building on these intuition, they added these two auxiliary classifiers in the two intermediate layers. This is the reason for the so-called early escape loss layers in the middle of the network in Inception. So the authors of the paper clearly say exactly that these classifiers take the form of smaller convolutional networks put on top of the output of Inception 4A and 4D modules. During training, their loss gets added to the total loss of the network with a discount weight. The losses of the auxiliary classifiers were weighted by 0.3. At inference time, these auxiliary networks are discarded. And then the total loss of the network is calculated following this formula, that is, total loss is real loss plus 0.3 into auxiliary loss 1 plus 0.3 into auxiliary loss 2. And we'll have this formula exactly implemented in code in a second. And another quick point that I have to mention while discussing Inception, that one of the key motivation of building the Inception module architecture was to reduce the computational complexity by using 1x1 convolution. And let's see how it reduces the total number of parameters. So on the top image here on the left, you can see that I have a single input that goes through a 5x5 filter and gives me an output, and here there is no 1x1 convolution because it's just one single filter of 5x5, and I have 32 of them. And in this case, the total number of operations or the total number of parameters will be calculated as below here. That is, I will have 28 by 28 into 32, which is my output, and multiply that with 5 by 5 by 192, giving me 120 million operations total. And that's too much. Now let's include a 1 by 1 conv in between these entire operation, and that's my image here at the bottom right corner. So again, I have the input of same image, that is 28 by 28 into 192 number of channels. I have a filter of 1 by 1, and I have 16 of these filter. Then I have an output from these operation, which is 28 by 28 by 16, and then I will have a bigger kernel or bigger filter, which is 5 by 5, and I will have 32 of them, and finally the output. And in this case, if I calculate the total number of parameters or total number of operations, that will be this calculation. That is, first I have the calculation for these 1 by 1 operation, and then to that I will add the number of parameters for the second conv operations. So for the first one, I will have 28 by 28 by 16 multiplied with 1 by 1 into 192, because the input image has 192 channels, so I will need to multiply it 192 times these 1 by 1 kernels. So this is this calculation. To that I have to add the second convolutions operation, which will be 28 by 28 into 32. That I have to multiply 5 into 5 into 16. 16 is a number of filter, and if we do all these multiplication and then add them, I will have 12.4 million operations. Now compare that with our initial, it was 120 million without the 1 by 1 conv layer, and now I have so much more reduced number of parameters, which is just 12.4 million operations. So that's one of the fundamental building block of Inception, that it brings in 1 by 1 convolution operations at various stages to reduce the total number of parameters, because it's a very deep network and we cannot everywhere use the larger 5 by 5 or 3 by 3 kernel size, because that will enlarge the total number of parameters so much it will almost become impractical, and also that is not necessary at all. And another quick point, that if you are thinking that how this number, that is this 32 number of filters here, or the 16 number of filters here, or 32 here was decided, that is, this is the number of channels or the number of filters, and it is a hyperparameter. So there is no mathematical formula to decide it. You have to decide based on your requirement, based on your input data set, or based on the result that you are getting, because it's just a hyperparameter and it needs to be tuned according to my situation. And also another point, that if you are thinking that after applying on the first image, for example, I have an input of 28 by 28 shape, and I'm applying 5 by 5. So how come I'm getting the output as well as 28 by 28? Because the output is supposed to get reduced. That's because I'm using, in both of these cases, I'm using padding equal to same. That will add zeros as padding, and it will add those padding exactly in the way so that my input shape and the output shape remains the same. And that's the very reason of using padding equal to same. And exactly in the bottom image as well, that's how I'm getting the input shape of 28 by 28 constant in every layer. Now finally, I am back to my VS Code to implement the entire architecture from scratch with PyTorch. I will have 3 files. One is GoogleNet.py. This Python file will have all the architectures, all the 4 classes. This is the main skeleton of my architecture. Then I will have a smaller Python file which will have just a single method, train model. This is just for training the entire architecture after that is built. And finally, a small Jupyter Notebook to see the actual training and the result of that. That is, this whole GoogleNet architecture I will implement on Cypher 10 dataset to see how that's working. So let's go back to my GoogleNet Python file. So in this file, I have 4 classes. One is conv block. Next one is inception. Third one is auxiliary. and fourth and the final one is the entire GoogleNet. So talking about conv block, it's the super simple class, the most simple one among all of them, which will have just three things, three layers: one convolution, that is conv2d, one batch normalization, and one ReLU activation. That's it. And it takes in channels, out channels, kernel size, stride, and padding as argument. And it stacks one layer on top of another. And finally, in the forward function, just a normal thing, regular thing I'm doing here, I'm invoking these three layers one by one, and output of the first layer is the input to my second layer, and the output from the second layer is the input to my third activation layer, and this is the final activation layer output is my final return from this class. And why this conv block is required is, if I go back to my architecture, that conv block is what I will implement here, that is in the stem part of the initial part of the network. And also each of these convolution layer inside my each of the Inception block will also be implemented with this class conv block, because here inside the Inception block, each of these conv, that is each of these blue blocks, actually implements a conv, batch normalization, and ReLU. It is clearly written in their paper as well. Let's go back to my annotated ones. One second. Yes, here they write very clearly that all the convolutions, including those inside the Inception module, use rectified linear activation. The size of receptive field in our network is 224 by 224. Okay, so this is the important part, that each of these convolutions have a batch normalization and have a rectified linear activation. Let's go back. Okay, so that's my conv block. Now come to the most important part, the Inception block, where the real juices are there. So remember, let's go to the paper to read few things. So if you look at this table, they mention, look at this part, that is I have one these hash 1 by 1, then I have hash 3 by 3, and then hash 3 by 3 again. So see the difference. This is the number of 1 by 1, and this 3 by 3 has a reduce word attached to it. Again, I have a hash 5 by 5 and with the reduced word attached, and then I have the 5 by 5. So what the paper talks about is that these number of 3 by 3 reduce and number of 5 by 5 reduce stands for the number of 1 by 1 filters in the reduction layer used before the 3 by 3 and 5 by 5 convolutions. So this column represents the number of, this column with the reduce word attached to the heading. So this reduce column and this reduce column actually denotes the number of 1 by 1 filters that I have to bring in before the 3 by 3 and 5 by 5. And why they are called reduce? Because the whole purpose of bringing in 1 by 1 conv is to reduce the number of parameter. And so my Inception class as well takes these similar kind of nomenclature here. That is, I have a num 3 by 3 reduce, I have a num 5 by 5 reduce argument, and of course I have these num 3 by 3 and num 5 by 5 because they actually represent the number of 3 by 3 filters and number of 5 by 5 filters. Apart from that, I have in channels and pool projection as well. All right, now this is relatively small class. Actually, I have just 4 output channels for each parallel block of network under the Inception. And note that I have so I have this block 1, block 2, block 3, and block 4. We will go back and see the image actually to make sense of these. And note that these blocks within Inception, they are actually running parallelly and not sequentially. So I'm going back to the architecture diagram. Let's look at a clean PDF. This one, yeah. So again, this is my whole architecture, and if you zoom in to a single Inception block, let's see one thing. So what I'm talking about is, one second. I have one conv block here. Then I have these two, which is sequential. And then I have these two, which is again sequential. And the last one is this. So exactly these four blocks I have to implement within my Inception class code. So the first conv layer goes alone. Then I have two conv, one conv input, one conv output goes to the next conv input. That is the first conv is a 1 by 1, and then I have the 3 by 3 conv, and the next sequential two layers are these first 1 by 1 conv. The output of this goes to the 5 by 5 conv, and the last one is first is a max pool, and output of the max pool goes to 1 by 1 conv. But these four blocks, they run parallelly. Within each block, these two operations, they are sequential. Just looking at the arrow, that will make sense. These two are sequential, but these four, 1, 2, 3, 4, they are parallel. Now let's see the code. Now it will all make sense. So the first block is a single conv block in channels, and it takes number of 1 by 1 filters. Kernel size obviously 1, stride 1, padding 0. The next block will be this one, and that first one is a 1 by 1 conv. The output of this goes to a 3 by 3 conv. So that's what I'm doing here. The first one is 1 by 1 conv, and that will take this num 3 by 3 reduce argument. That will again mean the number of 1 by 1 filters that will be there before the 3 by 3 filter conv. All right, the other things are obvious. The kernel size for the first layer is 1 because that's a 1 by 1 filter size. The next one, kernel size, is 3 because that's a 3 by 3 layer according to the diagram. Then comes my block 3, which is this one. And here, 1 by 1 goes to 5 by 5. That's what I'm doing here. The first one is 1 by 1 conv, kernel size 1. And the output of that goes to my next layer, which is a 5 by 5 conv. Here kernel size is 5, and stride remains 1 for all of them. And then the next block, that will be this one. Here first I have a max pool. Output of this max pool goes to the conv, and that's what I'm doing here. In block 4, first I have max pool, and output of these needs to go to my conv block, which will be kernel size 1. And the forward function implements these calculation, but note the difference with other forward function. Because they are parallel, here in the forward function I cannot have the output of previous layer go to the input of the next layer. No, it will not work like that, because it's a parallel. All of them are running parallelly. So I have the output of block 1, block 2, block 3, block 4 calculated with this same kind of lines, that is self.block1x, self.block2x. Then I have to concatenate these blocks with torch.cat, and then this is my final return, and this final result will go to the next layer. That is, after the result of these are concatenated as shown with these arrows, then this concatenated result goes for the next step of execution or next layer. All right, so that's I think that was enough of Inception block, and that really I think that was enough of explanation. I spent a lot of time on this. And then my auxiliary layer. Auxiliary class is much simpler. It is just a sequential block of sequential layers of operations. I have in the start, it starts with average pool with 5 by 5, then conv, fully connected, and here I will also have a ReLU implemented. So go back to the code. That's my auxiliary class, and so I'm starting with adaptive average pool. Then I have a conv2d activation with nn.ReLU, and then I have fully connected one, the first fully connected one. And if If you're wondering how I'm getting this number 1024 or how I am getting this nn.dropout 0.7 after the first fully connected, let's just quickly check the paper because it is very well explained here. Yeah. So here they say they talk about the auxiliary layer, fully connected layer with 1024 units and rectified linear activation. They clearly say that. And also a dropout layer with 70% ratio of dropped out outputs. And finally, a Nillion layer with softmax loss as a classifier, predicting the same 1000 classes as a main classifier, but removed at inference time. Yeah, so they very much say what I need to do in the auxiliary class. Yeah. So yeah, and then I have the forward function, just invoking this function one by one again. That here under the forward function, output of one layer goes to the input to the next layer. And so I first have the pool layer, then the conv layer activation, and here my conv layer ends because that was my last convolution layer, and then the activation, and then after this my first fully connected layer starts, and that's why here I'm doing a flatten, because the convolution will output a 4-dimensional tensor, but the fully connected layer, that is nn.linear, will require a 2-dimensional vector. And here I need to, that's the reason I need to flatten it, that is to make the 4-dimensional tensor to a 2-dimensional one. I have a separate video explaining that why and how exactly we do that. The name of the video is Input Tensor Shape in a Neural Network. Probably I will give a link in the description section. Anyway, because that's a little bit longer discussion, I don't want to take time on that. So that's after the flattening, I have my fully connected layer FC1, and then activation, dropout, and finally the FC2, fully connected layer 2, and that's my final output from my auxiliary. Okay, so now that my inception is done, conv block is done, and auxiliary is also done, I am fully ready to implement the entire things in my GoogLeNet architecture. And again, I will be following exactly these diagram here, this table, because here in this table they mention exactly what kind of things and what kind of input shape and filter size I have to choose, and I will follow these numbers pretty much blindly, and then you can actually check the architecture matches with this table. So first is conv block. So on the first convolution, looking at the table, I have to do a 7x7 filter with a stride of 2, and the output size from this needs to be 64. And so that's what I am doing here. First conv1, that is I'm implementing this conv block that we wrote earlier here. That takes in channels, out channels, kernel size, stride. So come back to my this line. So in channels 3, out channel 64, because that's what is written in the paper. Kernel size 7, stride 2, following the paper exactly. And then I need to do a max pooling layer with 3x3 and stride of 2. So I'm doing nn.maxpool 2d, 3, stride of 2, padding goes to 0. Similarly, the next few layer, conv2, conv3, pool 3, and that pretty much completes my stem part of the layers. Then I have my first inception block, which is Inception 3A. So for Inception 3A, if I go to the paper, this will be this layer. I have put this red border line around the numbers. So quickly take a note of this number. 64, that is this column, would be number of 1x1 filter. Then this column with the reduce word, this is a column for number of 1x1 filter before the 3x3 filter. This is 96 here. And 128 would be my number of 3x3 filter. Then again, this next column with the reduce word, that means it is a number of 1x1 filter before the 5x5 filter, and that is 16 here. And finally 32 is my number of 5x5 filter. So now let's go back. So my in channel should be 192 because that's coming from my previous pooling layer. And if I look at the previous pooling layer, the output was 192. That would be my in channels for my first inception layer. So that's why 192, number of 1 by 164, number of 3 by 3 reduce is 96, number of 3 by 3 128, number of 5 by 5 reduce is 16, number of 5 by 5 32, and pool projection is 32. Yeah, so it exactly matched the block. That's my Inception 3A. Now for Inception 3B again, this number is just according to the table. Let's go back to the paper. Yep. Inception 3B, 256 was the output channel number from Inception 3A. So that's why 256 would be my input channel for Inception 3B. Otherwise, in the same kind of way, 128, 128, 192, 32, 96. And that's my number, 128, 128 for reduce, 192. Again, for the next 5 by 5 reduce is 32. Finally, number of 5 by 5 is 96 and pool projection 64. All right, that's my Inception 3B. After Inception 3B, I have a pool layer according to the paper, max pool layer. So that's what I'm implementing it here. And then the next Inception, all of them, that is, I have total 9 Inceptions. All of them are implemented exactly following these numbers here. That is, this is your Bible, this table is your Bible while doing Inception V1 or GoogleNet implementation. And you can check these numbers because I will definitely give the link of this code in the description. You can check this number. I'm just following this paper. There's no point talking about it here again. And after all the 9 Inception, the last Inception was 5B. This is the 9th Inception. And so I have the last one here as well. And after that, I have a pool layer, dropout layer, fully connected layer, and then my 2 auxiliary layer, aux4a, aux4d. Okay, and after doing all these, this was all implemented, remember, with the conv block, which has an end or sequential, and the inception as well. These inception class as well has conv block under the hood. So now I have to do the forward function, implementing all of them one by one. That is, all these architecture that I build, I have to do invoke them one by one with the forward function, where the output of the previous layer will go to the input of the next layer. And you just have to be careful while implementing these structures. Otherwise, these lines of codes are just very simple. There's no complexity here. It is just one by one input output matching sequentially. Yes. Otherwise, yeah, another thing is to mention again, that is you have to be careful with the use of torch.flatten function when you are moving from one conv layer to your first fully connected layer. That is, before doing your fully connected layer, you always have to use torch.flatten, because you are converting your 4-dimensional tensor to a 2-dimensional one. Otherwise, from this forward block, I am outputting 3 things out: aux1, aux2. Remember, we need these because the loss function for Inception module is a combination, or is a weighted average of all these 3 things. So I have to include the real losses and also the weighted losses from aux1 and aux2. So that pretty much complete my network architecture of GoogleNet. And now only thing I have to do is do my train function and implement this whole architecture on Cypher 10 dataset. So let's go to my train file. Train file is just the standard boilerplate code, although it looks long, but it's just standard boilerplate code that I am creating. I'm starting with a data loader and then running 2 loops. The outer loop will be for each epoch and the inner loop will be for each batch. And then I will calculate batch loss, and from each batch loss I will calculate epoch loss, and I will keep a track of all the epoch losses in a list, and that's what this train method will do. But anyway, let's quickly go through the train function so that we understand it in detail. All right, so the train model method takes the model, train loader, validation loader, criterion, which is my loss function, and optimizer as the arguments. And because now inside it, because I'm doing it for Cypher 10 dataset, which has 50,000 images in the train set and 10,000 images in the test set. So from train samples itself, I am keeping 45,000 for my training and 5,000 for my validation. And just declaring here in this line some two variables to hold the epoch losses into list, so that later I can plot them to check their movement across the epochs. All right, and now I have two loops from outer and inner loop. Outer loop will be for each epoch, and the inner loop which will be for each batch. And then to the each batch I am passing so here I am actually looping over the train loader, which is coming from my data loader from my data set. And of course here I am moving all of these tensors to the same device. That's very much standard practice in PyTorch. And first here optimizer.0 grad, because for every mini batch during the training phase, we typically want to explicitly set the gradients to 0 before starting to do the back propagation. And this line is where the model is invoked, and to the model I'm giving the inputs to get my three tensors containing the predictions, which will have my real predictions inside it, and then auxiliary from the auxiliary class predictions and auxiliary class 2 predictions. And I also, because I have these three variables for three different classes, I also need to do the losses for three of them: real loss, auxiliary loss 2, by invoking my criteria. And criterion will be this is a multi-class classification problem. So my criteria will be chosen in this Jupyter Notebook, and that will be nn.cross entropy loss. What I'm doing it, okay, I'll come back to that later. Let's go back to my train.python file. Yes, and the loss, it is very well written in the paper. It is a weighted average loss. So the total loss from the network will be the real loss plus only 30% of the auxiliary loss 1 and 30% of auxiliary loss 2. And then I will do back propagation and also update the weights by invoking the step method of PyTorch on the loss. So loss.backward and then optimizer.step. Then update the running. Then I have to do get the actual predicted values and also update the correct values, that is which will be needed for calculating the accuracy. So here we're invoking torch.max on these prediction 0, which I got here. On that I have to apply torch.max to get the maximum value from the vector, which will be my prediction from the model. And to the torch.max I am giving these dim equal to 1, that is it will calculate the max on the dimension equal to 1, that is across the rows. And then my correct train will just be equal to where the ground truth is equal to the predicted value. My ground truth is my labels, which is coming from here. When I was looping over iterating over my train loader dataset, and predicted value is just what I calculated in the previous line. And yeah, so that's my corrects. And then I have to also calculate the entire batch loss, because up to this point this loss is an average loss. I have to multiply this average of the batch, that is multiply each average batch loss with batch length, because the batch length because this loss by definition, by default in PyTorch is the average, but I have to kind of unaverage it. So that's why I have to multiply it with the batch length. There is a number of samples in the batch, and I will get the batch length by doing input.size and taking the 0th element. And what is my inputs? This is my inputs. That is when I was iterating over train loader, I will have labels and I will also have inputs. and if I do the get a shape of them, and the 0th element will give me the total number of samples in that batch. And that's why here in this line, train running loss, I am actually multiplying these batch loss data with inputs.shape 0. That will give me the unaveraged loss, and I'm accumulating it over each batch. Remember this, I am doing a plus equal to, it is accumulating these numbers while I am going through batch by batch. Alright, so here with this line, the inner loop gets over. Now I am outside that loop, so that I can, here in this line, I can actually calculate the numbers for this epoch. And my train epoch loss will be this running loss divided by train samples number. And train sample number, I think it's coming from, here I declared it to be 45,000. All right, with that, my train loss is done, and my correct train also were calculated earlier, so I can do the training accuracy calculation by doing this simple division, that is correct train divided by train sample number. And also in this line previously, before this line, and very importantly, to this history train epoch loss history variable, I have to keep appending the train epoch losses, because that's very important to do your plotting at the end of the entire training. All right, so that was my training part, and also I want to calculate these loss and accuracy for my validation set. And for this is that block to calculate the same exact calculation on the validation set. So it is just the same exact code. Only thing difference is that here there is no batch by batch calculation, because here it is just a validation set. So there is no training going on here. And that's also the reason I'm setting torch.no-grad. It will switch off the gradient calculation, because now I'm kind of in the evaluation mode. Otherwise, here again, I'm running these loop over the validation loader, but there is no batch by batch calculation here. So I'm getting all my inputs, all my labels, and then I'm getting all my predictions. Also, the same way, I'm getting real loss, auxiliary loss 1, auxiliary loss 2, calculating the overall loss. Then I am on averaging the validation loss by doing the same calculation, that is multiplying the average loss with the input.shape 0 and accumulating this number. And finally, I'm calculating validation accuracy and validation loss. All right, so as the last steps in this function, I need to save this model with state-dict method of PyTorch, because when I will be invoking this train model on my test data set, then I will need this saved model, obviously. Anyway, these are just like kind of obvious steps at the end of a training, that you save your model with state-dict. And I'm saving it in I was running this entire thing in Google Colab, so I'm using this particular directory in Google Colab. And later, while doing the test phase, while doing invoking this train model, I will load this saved model there. That function will be inside my Jupyter Notebook. And finally, from this train method, I am returning train epoch loss history and validation epoch loss history, and that's pretty much my train method. Now let's get into Jupyter Notebook. So initially I was just loading my Google Drive in this first cell. These are all boilerplate things, so no point in talking about that. And importing all the important libraries. I think I imported all these extra ones that I don't need, so I'm just deleting them. Yeah, this also I don't need. All right, now so my model, so I'm importing from those two files, googlenet.py and train.py. I'm importing everything with the star, and then I'm declaring this model variable to be this GoogleNet class object of this GoogleNet class. And then to that model, I'm passing random data, random tensor, random tuple as tuple to get initial summary of my model, and that how this performs. And this is a summary I got. Let's open this in a text editor. Yeah, So this is that entire architecture of my network, and it's pretty deep network, you can obviously see. And starting is it will give you all the output shape and parameter, etc. So yeah, well, when you run this, if you run this notebook, you definitely need to check this. For now, I'm just closing it. All right, that was my summary, but now I need to do the actual training on Cypher 10 dataset. So for that, I need to load my Cypher 10 dataset, and that's what I'm doing here with this little function. A very simple function here. All I'm doing is just invoking my torch vision.dataset, and then invoking Cypher 10 dataset to that method, and that will pool the entire Cypher 10 dataset into the directory that you mentioned here. And because I am getting both the train and test dataset, in the first line I'm mentioning train equal to 2, and for the test, train equal to false. And yeah, and for the transform, only very basic transform I'm applying, that is transform them to tensor and also normalize them to a mean of 0.5 and standard deviation of 0.5 as well. All right, and because I was using Google Drive to keep my Cypher 10, so that's why these location is my Google Drive location from my collab. And then I'm splitting this data set because I need a validation data set as well from the same train. So that's why I'm using random split, which will split the train data set to 45,000 for training and 5,000 for validation. And then some basic printing to check my shapes of the data set, etc. And batch size I'm using 128. And finally, this is important, 3 lines. Obvious, you have seen it probably multiple number of times, that you will be using data loader to have full control over your data set, the way that it will be fed into your model batch by batch, and keeping shuffle equal to true, and some other control also if you want to give. Data loader is super important. So yeah, so with the data loader, basically I am getting the whole data batch by batch to be fed into my training module. And finally, from the Cypher data loader method, I'm just returning these 3 data loader. That is train loader, validation loader, test loader. Here in the next cell, I'm invoking them, so I will have the result. So we can see that image shape of random sample image is 3 by 32 by 32. That's the shape of Cypher 10. And my training set is 45,000, validation 5,000, test 1,000. All looks good. And finally, before starting the training, I have to mention the criterion and optimizer. As I said previously, it's a multi-class classification problem where the purpose is to classify them among 10 different classes of Cypher images. So I have to use cross entropy loss. And for the optimizer, I'm using optim.adam optimizer. Learning rate, I'm using the standard one, 0.001. And then I'm invoking my train model that I defined in this file. And to the train model, you just need to pass the model which you have already declared here at the top. Where did that go? Here. Model is my GoogLeNet model. And then the train loader, validation loader, criterion, optimizer, and it will start the training. In Google Colab, it took something like, I think, 20 minutes to run 15 epochs. And at the end of 15 epochs, I then ran the evaluation model. And remember what we mentioned, that during the training, we saved our model with state_dict, and now with load state_dict, I am loading that earlier saved train model. On this, I will be invoking my test data set. So here in this line, my previously trained model is loaded. And now the final step, the absolute final step, is to evaluate on my test data set. And here again, this block of code is exactly like my block of code for the validation part, that is here. Only difference is that it is even more simpler, and there is no separate loss calculation as such. So here I'm just doing a torch.nograd to switch off the gradient calculation. Then I'm looping over the test loader data loader. which will iterate over this 10,000 number of samples images in my test data set, get my predictions by invoking the pre-trained model, then get my actual predicted classes with the torch.max, get my actual corrects by doing this calculation where the predicted is equal to the labels. Finally, calculate the accuracy by dividing the total corrects by number of test samples. And when I ran these for 15 epochs, I got a test accuracy of 0.7571. Remember, it's not too good but not too bad as well, because I ran only for 15 epochs, and also I did not do any sort of good transformation of data. There is no data preprocessing at all. I just applied a normalization and that's it. But with little bit more transformation on data, that is pre-processing of the data. And also, if you run these notebook for like 70-80 epochs, you definitely, this accuracy will be improved substantially. All right, so that's because I did not do all those extra things like pre-processing and running for large number of epochs, because here in this video my purpose was to implement the entire GoogLeNet architecture from scratch. Anyway, this video became much longer than I thought it to be. So that's my final result, and yeah, that's the entire GoogLeNet architecture implemented from scratch. And obviously, I will include the entire source code link of my GitHub repository in the description of the video. That pretty much wraps up this video, and all my upcoming videos will all be on some great computer vision projects and algorithm with PyTorch and Tensorflow. So stay tuned, and if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. Thank you for watching.